March 7, 1943. North Atlantic, Mid-Ocean Convoy, HX2-29. Corvette HMS Sunflower detected a submerged contact at 2,400 yards. The ASDIC operator reported bearing, range, and contact classification. Submarine. The U-boat had no idea Sunflower had found it. German hydrophones could detect escort propellers at 1,000 yards maximum. ASDIC could detect U-boat hulls at 2,500 yards. The British had a 2.5 to 1 detection range advantage. U-531 never knew what hit it. 3 depth charge patterns later, the U-boat surfaced, crew abandoned ship, and another German submarine became a war grave. ASDIC had turned submarine warfare from hide-and-seek into target practice. The British called it ASDIC. The Americans called it Sonar. The Germans called it unfair. Active submarine detection using sound waves gave Royal Navy escorts the ability to find submerged U-boats before U-boats could detect them. The range advantage was decisive. German passive hydrophones could only listen for propeller noise. ASDIC could send out sound pulses and measure the return echo. Active versus passive, hunter versus prey. The technology gap determined who won the Battle of the Atlantic. This wasn't incremental advantage. This was technological dominance that German engineering couldn't match. ASDIC operators trained for months. German hydrophone operators trained for weeks. ASDIC could determine range, bearing, and depth. Hydrophones could only guess direction. ASDIC worked in conditions where hydrophones were useless. British convoy escorts hunted U-boats with precision. U-boats hunted convoys by guesswork and luck. The detection range difference meant life or death for convoys, U-boats, and the war itself. The problem began in 1914. World War I submarines proved conventional detection methods useless. Visual lookouts couldn't see periscopes in rough seas. Hydrophones could hear submarines but couldn't locate them precisely. U-boats sank merchant ships faster than Britain could build replacements. The convoy system reduced losses, but escorts needed technology to hunt submarines underwater. Listening wasn't enough. British scientists needed active detection. They needed a way to find submarines that didn't want to be found. German U-boats in World War I had crude hydrophone systems. Passive listening devices detected propeller noise and machinery sounds. Effective range, 500 to 1,000 yards in calm conditions, much less in rough seas. Bearing accuracy, approximate at best. No range information. Hydrophones told U-boat commanders that escorts were nearby, but not where exactly or how close. Enough information to evade, not enough to fight effectively. British escorts had similar hydrophones, same limitations. The technological stalemate meant submarines held the advantage. They could dive, hide, wait. Escorts could search, guess, hope. Merchant ships died. The German submarine campaign of 1917 nearly starved Britain. Post-war analysis concluded that submarine detection was the critical technical problem. Solve detection, win the next submarine war. British scientists started work in 1918. The anti-submarine division of the Royal Navy established research programs. The name ASDIC came later, supposedly from Allied Submarine Detection Investigation Committee, though some historians dispute the exact origin. What mattered was the research result. Active sound detection using transmitted pulses and echo returns. The physics were simple in theory, complex in practice. Send a sound pulse underwater. If it hits a solid object, it reflects back. Measure the time between transmission and return. Calculate range from sound speed in water, approximately 1,500 yards per second. Measure the bearing of the return echo. Plot the contact, attack. The engineering challenges were massive. Generate sufficient sound energy to reach useful ranges. Build transducers that could transmit and receive efficiently. Filter return signals from background noise. Train operators to interpret echoes. Overcome thermal layers, salinity changes, and water conditions that bent sound waves unpredictably. British researchers solved each problem through systematic experimentation and development. Early ASDIC sets appeared in the 1920s. Type 116, the first production model, went to sea in 1923. Operating frequency is 25 kHz, well above human hearing. Detection range, 1,000 yards maximum in good conditions. Bearing accuracy, plus or minus 5 degrees. Primitive by later standards, revolutionary compared to hydrophones. If for the first time, escorts could find submerged submarines at range and attack with precision. Development continued through the 1930s. Type 123 appeared in 1934. Improved transducer design, increased range to 1,500 yards. Better signal processing improved bearing accuracy to plus or minus 2 degrees. Type 123A, introduced in 1937, added depth measurement capability by analyzing echo characteristics. Now, escorts could determine not just where the submarine was, but how deep. Type 127, introduced in 1939, was the standard convoy escort ASDIC when war began. Operating frequency, 20 kHz to 30 kHz, adjustable. Maximum detection range, 2,500 yards in ideal conditions, 1,500 to 2,000 yards typical. Minimum detection range, 200 yards, the transducer's blind spot. Bearing accuracy, plus or minus 1 degree. Depth estimation, accurate to within 50 feet. Transmission rate, 1 pulse every 3 to 5 seconds, giving time for echoes to return before the next pulse. The transducer was the critical component. Quartz crystal mosaics generated sound pulses when electrical current oscillated through them. The same crystals detected returning echoes and converted them back to electrical signals. The transducer mounted in a retractable dome under the ship's hull, protected when retracted, exposed when operating. The dome could train left or right to search different bearings, but couldn't look directly ahead or astern, limiting search arcs. Type 144 and Type 145, introduced in 1942 and 1943, represented wartime refinements. Higher frequencies, up to 50 kHz, improved resolution but reduced range. Better electronics improved signal-to-noise ratios. Faster training speeds let operators search wider arcs. Maximum range remained around 2,500 yards, the practical limit for available technology and power levels. German hydrophone systems evolved more slowly. Gruppenhochgerät, or GHGs, was standard U-boat. Hydrophone equipment, passive arrays of multiple listening devices mounted in the bow. Operating principle, detect propeller noise, machinery sounds, water flow around hulls. Effective range, 1,000 yards maximum in calm water, 500 yards in rough seas. Bearing accuracy, approximate, requiring manual triangulation by comparing signal strength across different hydrophones. No range information. No depth information. Pure listening, no active transmission. The German Navy knew about active sonar. Captured British equipment revealed ASDIC principles. German scientists understood the physics. German industry could build transducers, but Germany never deployed effective active sonar on U-boats or escorts. 3 reasons explain this failure. First, manufacturing precision. ASDIC transducers required extremely precise quartz crystal cutting and assembly. Tiny variations in crystal dimensions caused frequency shifts and power losses. British manufacturers had years of experience and quality control systems. German industry, under wartime pressure, couldn't match the precision consistently. Second, operator training. ASDIC required extensive training. British operators attended specialized schools for 12 to 16 weeks. They practiced on simulators that reproduced echo characteristics. They trained at sea with practice submarines. They learned to distinguish submarine echoes from wrecks, rocks, fish schools, and thermal layers. German hydrophone training lasted 4 to 6 weeks with less systematic instruction. Active sonar required even more training to interpret echoes correctly. Germany couldn't spare the time or instructors. Third, doctrine. German submarine doctrine emphasized stealth. U-boats hunted by staying hidden. Active sonar transmission revealed the U-boat's position to any listening hydrophone. British escorts didn't care about revealing their position. They wanted to find submarines. German submarines couldn't risk giving away their location to use active sonar, even if they had it. Doctrine prevented technology adoption. The result was a fundamental detection asymmetry. British escorts could detect German U-boats at 2,500 yards. German U-boats could detect British escorts at 1,000 yards. The 2-to-1 range advantage gave escorts time to maneuver into attack position before U-boats knew they were hunted. The advantage grew worse for U-boats when multiple escorts cooperated. ASDIC operators became the critical operators in convoy battles. Each escort carrier, destroyer, frigate, or corvette had trained ASDIC operators. They sat in darkened compartments, headphones on, watching cathode ray displays showing echo returns. The transmitted pulse was audible, a sharp ping through the water. The return echo was distinctive. A solid contact gave a clear, ringing return. Wrecks gave fuzzy echoes. Fish schools gave scattered returns. Thermal layers gave false contacts. Experienced operators learned to distinguish real submarines from false contacts within seconds. Standard ASDIC search pattern was the expanding square. The escort steamed on one bearing for a set time, transmitted ASDIC pulses continuously, then turned 90 degrees and repeated. Each leg was longer than the previous, creating a growing search box. If ASDIC detected a contact, the escort turned toward the bearing, increased speed, and began the attack approach. The attack procedure was systematic. Confirm contact classification as submarine. Determine range by echo timing. Determine bearing by transducer direction. Estimate depth by echo characteristics. Plot attack course. Increase speed to attack speed, typically 15 to 20 knots. Continue ASDIC tracking during approach. At 500 yards, lose ASDIC contact as the submarine enters the dead zone under the ship. Continue on last known bearing. Drop depth charge pattern based on calculated submarine position and depth. Depth. Charges were the weapon. Mark 7 depth charges carried 300 pounds of Amdex explosive, set to detonate at predetermined depth, 50 to 500 feet. Dropped in patterns, 5 charges for corvettes, 10 or 14 for destroyers. Pattern spacing, 40 to 60 feet. Lethal radius, 20 feet for direct kill, 50 feet for severe damage, 100 feet for minor damage. The goal was to bracket the submarine in 3 dimensions, ensuring at least one charge detonated close enough to rupture the pressure hull. ASDIC made depth charge attacks effective. Without ASDIC, escorts dropped charges where they thought the submarine might be. With ASDIC, escorts tracked the submarine continuously until entering the dead zone, then dropped charges on calculated positions. Hit probability increased dramatically. U-boats learned that ASDIC contact meant probable death. Specific convoy actions prove ASDIC effectiveness. Convoy SC-104, October 1942. Corvette HMS Vervain detected U-boat contact at 2,000 yards. Approached, attacked, no immediate result. Regained contact at 1,800 yards. Attacked again. U-619 surfaces, crew abandons ship, scuttled. ASDIC detection at range enabled persistent attacks until kill achieved. Convoy HX-237, May 1943. Frigate HMS Lagan detected contact at 2,300 yards. Coordinated attack with HMS Vidette. First depth charge pattern damaged U-boat. Second pattern at 1,500 yards after ASDIC reacquisition. U-209 surfaces severely damaged, crew surrenders. ASDIC enabled precise tracking through multiple attacks. The statistics prove technological superiority. In 1941, before widespread ASDIC deployment on corvettes, U-boats sank merchant ships at 4-to-1 ratio compared to U-boat losses. In 1943, after all escorts carried ASDIC, ratio reversed to 1-to-1. By 1944, escorts sank U-boats at 2-to-1 ratio. ASDIC turned the Battle of Atlantic from German advantage to Allied victory. German countermeasures attempted to defeat ASDIC. Pillenwerfer, or bold, was a chemical decoy. Compressed calcium hydride canisters ejected from U-boats created bubble clouds that reflected ASDIC pulses. Effective briefly, but trained operators recognized decoy echoes as fuzzy and indistinct compared to solid hull returns. British response: attack both contacts. If one was a decoy, the other was probably the real submarine. U-boats also tried sound-absorbing coatings. Rubber tiles called alberich covered some U-boat hulls to absorb ASDIC pulses rather than reflect them. Reduced echo strength, but didn't eliminate detection. Tiles were fragile, fell off in rough seas, required constant maintenance. Few U-boats received full coverage. British response: increase ASDIC transmission power. German attempts to jam ASDIC failed. Active sonar. Transmitted at high power, making jamming extremely difficult. U-boats would need to transmit sound at higher power than ASDIC sets to mask echoes, revealing their position. Jamming wasn't practical. The British improved ASDIC continuously. Type 147, introduced in 1944, used higher frequencies for better resolution against snorkeling U-boats. Type 148 combined ASDIC with a head-throwing weapons like hedgehog and squid, eliminating the dead zone problem. Post-war sonar systems all descended from British ASDIC principles. Compared to American sonar development, U.S. Navy QC sonar was based directly on British ASDIC. American manufacturing produced QC sets in larger quantities, but the technology was British. American operators trained with British instructors using British methods. The Anglo-American Anti-Submarine Warfare Partnership worked because both navies used compatible ASDIC technology and doctrine. ASDIC had limitations. Performance degraded. In shallow water, where bottom echoes confused returns, thermal layers, temperature changes at different depths, bent sound waves, and created false contacts or masked real submarines. High ship speeds created flow noise that reduced sensitivity. Rough seas scattered sound pulses, reducing range. British doctrine adapted to ASDIC limitations. Convoys steamed at slow speeds, 9 to 12 knots, allowing escorts to use ASDIC effectively. Escorts practiced in different water conditions to understand local thermal layer effects. Training emphasized recognizing and compensating for environmental factors. Operators learned that ASDIC was a tool, not magic. Used correctly within its limitations, ASDIC was decisive. Used carelessly, it gave false confidence. The Escort crew training program produced ASDIC operators faster than U-boat training produced crews. HMS Osprey at Portland was the Royal Navy's anti-submarine school. Operators trained on land simulators, then at sea with practice. Submarines. Training included physics of sound propagation, equipment operation, echo interpretation, attack geometry, and coordination with weapons systems. Graduation required demonstrated proficiency in detecting and tracking submarine contacts. Compared to U-boat hydrophone training, operators learned equipment operation and basic listening techniques, less systematic, less comprehensive, shorter duration. U-boat crews had higher overall skill, but specific anti-submarine detection technology training favored British escorts dramatically. The technological gap explains why Germany never won the submarine war. U-boats had speed, range, and torpedo firepower advantages early in the war, but they couldn't hide from ASDIC. Detection range advantage meant escorts found U-boats before U-boats could set up attacks. Once detected, U-boats faced coordinated attacks from multiple escorts with precise depth charge delivery. The 2,500-yard ASDIC range versus 1,000-yard hydrophone range difference determined every convoy battle outcome. Post-war analysis confirmed British technological superiority. Captured German naval officers acknowledged ASDIC effectiveness and German inability to counter it. German scientists admitted they understood the principles but couldn't match British manufacturing quality or operator training. The technology gap wasn't theoretical understanding. It was practical implementation and doctrine. Modern sonar descends directly from British ASDIC. Active sonar on submarines, surface ships, and aircraft uses the same principles. Transmit sound pulse, detect return echo, calculate range and bearing. Frequencies changed, electronics improved, computer processing replaced human operators for some functions, but the fundamental technology came from British development in the 1920s through 1940s. The verdict is clear. ASDIC gave the Royal Navy decisive advantage in submarine detection. 2005. 100-yard range versus 1,000-yard range meant British escorts found German U-boats first. Finding first meant attacking first. Attacking first meant killing first. The technology gap enabled Convoy systems' success. Without ASDIC, convoys would have suffered unsustainable losses. With ASDIC, escorts hunted U-boats systematically and won. German hydrophones were adequate for submarine use. They detected threats at useful ranges for a vessel trying to hide, but they couldn't provide the range, bearing accuracy and depth information needed for effective anti-submarine warfare. Passive listening wasn't enough. Active detection was required. Britain had it. Germany didn't. That technological difference decided the Battle of the Atlantic. British scientists developed ASDIC. British manufacturers built it to precision standards. British schools trained operators systematically. British doctrine employed it effectively within its limitations. German scientists understood active sonar, but couldn't replicate it. German industry couldn't match manufacturing quality under wartime conditions. German training programs couldn't spare time for extensive operator education. German submarine doctrine made active sonar tactically unusable even if available. The result? Technological dominance that determined the war's outcome. U-boats couldn't hide from ASDIC escorts. Convoys got through. Britain stayed in the war. Allied armies invaded Europe with supplies protected by ASDIC-equipped escorts. British naval technology won the Battle of the Atlantic. ASDIC detected U-boats at 2,500 yards, while German hydrophones could only hear escorts at 1,000 yards. That 2.5 to 1 advantage turned submarine warfare from German strength into Allied victory. British engineering superiority, proven underwater, one echo at a time.